Great pleasure to speak here. My apologies because of when Shabbat was and scheduling, that today's the only day I came. I was probably too ambitious in preparing this talk. I'm not sure I'll get all through it. And I may go a little fast, so I will post the slides on my website if anyone wants to see them. This, of course, I am delighted with the new building, and I want to thank the donors for their generosity. I should begin by saying in the title, it should perhaps be rather called 70 years than 50 years. I picked 50 because it's a rounder number than 70, and because it was exactly 50 years ago that I did my earliest work on the subject. But in many ways, the birth of the subject was Katos' work on the self-adjointness of atomic Hamiltonians roughly 20 years earlier. I say roughly because it's actually difficult to assign a date to when you want to say Katos' theorem was. Like Newton, Kato did his fundamental work on the physics of Coulomb potential while he was away from university. He was actually evacuated to the Japanese countryside during the war. At the time when the war, with the US at least, broke out in 1941 and they started evacuating people, he was a graduate student in physics at the University of Tokyo. After the war, he returned as a graduate student of physics. He found his theorem about 1944, submitted it in 1947 to Physical Review, at which point he was a 30-year-old graduate student. And not surprisingly, Physical Review couldn't figure out what to do with this strange manuscript. For now, the details are a little murky. I say for now because, in fact, a year and a half ago, Katos' wife passed away, and a lot of Katos' papers she actually left to some of his former graduate students. This includes his notebooks from the war, which I believe have already been published in Japanese, and they promise an English translation. And I was told there's some very interesting correspondence between von Neumann and Kato, which they also promised to publish, and it should be much clearer exactly what happened. But in fact, eventually von Neumann got involved. The manuscript was lost several times, and this was pre-Xerox days. So, right, he presumably had a copy that he made of the original manuscript, but then he had to make another copy. And eventually it was published in the Transactions of the AMS in 1951. But 50 years is actually not an unreasonable number. Before 1970, much of the research was actually just refining Kato's original result, plus some work on scattering theory. It was basically by Kato and his graduate students in Japan and a few groups in Germany. Around 1970, there was an explosion of results that was connected with a flowering of mathematical physics associated with schools founded by Biermann, Yost, Kastler, and Whiteman in Russia, Switzerland, France, and the US. In particular, there was a golden era in Princeton that was begun by my advisor, Arthur Whiteman. He's known primarily for his work in quantum field theory, but he had very broad intellectual interests, had a wide influence through his graduate students in areas as wide, and you'll see the names of the students, as quantum field theory, classical mechanics, statistical mechanics, C-star algebras, renormalization theory, and Schrodinger operators. There was lots of low-lying fruit and an explosion of research in the 1970s. I'm going to describe some of the high points of the developments, many of them produced in Sloan Hall, not in the 70s. And because there's so much material, I won't attempt to give any proofs or to explore certain sub-developments, and in particular, I'll skip entire areas say nothing about Schrodinger operators with electric and magnetic fields or about the theory of resonances. Following instructions from Dinnicker, I've tried to focus on areas with interesting open problems. However, most of these open problems are not being actively worked on because no one knows how to attack them. But I invite the people in the audience to work on them. So a Schrodinger operator is the Hamiltonian of a system in non-relativistic quantum mechanics. So the theory of Schrodinger operators essentially includes the mathematical analysis of the physics behind atoms, molecules, and solids, everyday material. You may be puzzled about why I say 50 or 70 years, because after all, von Neumann was in Göttingen with Born and Heisenberg, and Weil was at ETH with Schrodinger, and they actually produced books on the mathematical foundations of quantum theory around 1930, long before Katos' work. To understand why one only dates the theory I'm going to talk about from Katos' work, it pays to think about mathematics behind classical mechanics. There's what I call first-level formalism, which in modern language is the study of Hamiltonian flows on symplectic manifolds. But very different is celestial mechanics, which is the study of the explicit behavior of classical systems when you have actual Coulomb potentials. In the same way, what Weil and von Neumann discussed is what I call the first-level foundations of quantum theory. The Hilbert space framework, the special role of self-adjoint operators, and the unitary groups they generate. And Schrodinger operators, on the other hand, involves what I call the second-level foundations, that is the explicit study of the differential operators and the flows they generate that are of relevance not in general quantum theory, but specifically to non-relativistic quantum mechanics. They center primarily around Coulomb potentials, but much of the literature studies more general potentials. Partly the general considerations is motivated by mathematical curiosity, but also it turns out much of physics involves approximation to underlying Coulomb systems which lead to non-Coulombic potentials. For example, if you consider a large chunk of salt that actually is physically describing a large number of sodium nuclei, chlorine nuclei, and lots of electrons, but in a thermodynamic limit, in an infinite volume limit, and in a one electron approximation, you instead look at a single electron moving in a periodic potential, which is certainly not purely Coulomb. So the more general set of potentials and more general problems are of interest because we often approximate. In nature, virtually everything is controlled by Coulomb potentials, but we often approximate by things that are not Coulomb. About 1905, Hilbert proved the spectral theorem for bounded self-adjoint operators. There were important refinements by Rees in the next 10 years. In 1926, von Neumann went to Göttingen. He'd done his thesis in mathematical logic, and he went to Göttingen to work with Hilbert, who was then primarily focusing on, in fact, mathematical logic. However, in Göttingen at the time, there was lots of excitement connected with work on quantum theory, and so von Neumann decided, instead of continuing his work on logic, to look at the mathematics behind quantum theory. Particularly, he realized that it was important to extend Hilbert's spectral theorem to cover unbounded operators. And but it's true that while quantum mechanics was motivating his work, these notions were very much in the air. For example, Whitner, who later spent most of his career at Hopkins, independently of von Neumann, developed a lot of the results in von Neumann's basic paper on unbounded operators without knowing anything about quantum mechanics. I'm not going to try to give a mini course on the difference between Hermitian and self-adjoint operators, but I will tell you that for an unbounded operator, they come with domains of definition. If you take something like Laplacian, you can't hope to reasonably apply that to any function in L2 and stay inside of L2. So they have domains of definition, and the issue of self-adjointness means you've described the domain precisely, neither too small nor too big. For differential operators, this often has to do with getting the right set of boundary conditions. Both Weil and von Neumann realized once you had self-adjointness, you could prove existence and uniqueness of solutions of the time-dependent Schrodinger equation and get a unitary propagator, so that the self-adjointness question was absolutely fundamental to understanding the underlying physics. And von Neumann also realized once you had a spectral theorem, you'd have, once you had self-adjointness, you'd get a spectral theorem and associated spectral measures. So the Hamiltonian for atoms in Schrodinger's quantum mechanics, at least if we assume the nuclei have infinite mass, is given by the following form. So this is an atomic system. You have n particles with coordinates x1 to xn, which are three-dimensional vectors, and the Hamiltonian has this form. There are complicated singularities when particles come together. If you just have a single particle, again with an infinite nuclear mass, that means two particles, then of course there's only a simple singularity, but if you have lots of particles, you have the complication that you may have more than, you may have several particles going to zero, and so the singularity structure is very complicated. And at a physical level, the uncertainty principle is supposed to solve the problem of the unbounded potentials. What Kato proved is that on the natural domain of the free Laplacian, which I won't try to explain, but in terms of Fourier transform, it's described by this relation, this atomic Hamiltonian is well defined and is self-adjoint in this technical problem. This is perhaps the most important result in the mathematics of non-relativistic quantum mechanics. One can appreciate it by comparing it to the analog of celestial mechanics, which concerns the existence of global solutions to Newton's equations for n-point particles with gravitational interactions. There aren't, of course, always global solutions in that case, because if you have particles coming together, then you don't know what to do with the dynamics. But the obvious analog of the self-adjointness result is that global solutions should exist for almost all initial conditions. And this is a problem, this is a result that's known for 2, 3, and 4 particles, but remarkably, the first open problem I want to mention is that it's not known that gravitational equations have solutions for almost all initial conditions for 5 or more particles. It's not even known that there can't be a positive initial set of initial conditions where particles escape to infinity in finite time. You have actually funny examples where you have 2 pairs of particles coming together, another particle, a 5th particle that goes between them. As these particles go together, everything gets higher velocities, and you can imagine going out to infinity in finite time. And I believe such solutions are known to exist, but it's not known they don't correspond to positive. So this is the first open problem for the Gordian story. As Kato remarked in his Wiener Prize lecture, the proof of his signature theorem isn't hard. It has 3 steps. First, you prove a perturbation result that says Self-adjointness is preserved under perturbations if the perturbation can be suitably controlled by the unperturbed operator. This is known now as the Kato-Relic theorem. Kato found it in this 1944-45 period. Relic actually already published it in 1939. The second result you need for particles in 3 dimensions, the kinetic energy is dominates the potential energy in a way that one can apply the Kato-Relic theorem. Physically, this comes from a version of the uncertainty principle. Kato and most modern approaches use Sobolev inequalities to state this. Those were already known by the late 1930s. For Coulomb potentials, one can instead use Hardy's inequality in a form that was already written down in Courant-Hilbert. And Relic used related ideas in work about 1942. So the first 2 steps were, in some sense, Relic must have known. And then you need an observation that essentially says that by changing variables, if you know how to handle 3D problems, you can actually handle individual pieces of the Coulomb Hamiltonian by integrating out the other variables. This observation you can regard as trivial, but it's not trivial until you realize it. It's still remarkable it took 20 years for this problem, which was clearly an important problem when von Neumann wrote his book, 32 book. It took 20 years for this problem to be solved. Of course, one shouldn't remember that there was lots of other stuff happening from 1939 to 1945 that prevented people who might have solved this from instead working on this. But another possible factor was probably von Neumann's attitude. I heard from Bogman, and Ruel told me he heard from Yost, that as late as 1948, von Neumann was telling young people that self-adjointness for n-body atoms was an impossibly hard problem, and that it was even a difficult problem for hydrogen. This is puzzling because for hydrogen, you can solve this by separating variables into ordinary differential equations and using ideas that were already very well understood in the mathematical literature. So it was probably useful that Kato was isolated and didn't know that the problem was an impossibly hard problem. There's a huge literature on self-adjointness. I want to limit my discussion to self-adjointness to one other result where, again, Kato's the hero. I'll discuss the general case of this involves Hamiltonians of the general form minus Laplacian plus V. In the 10 years following 1951, various people showed that the natural restriction on LP properties when you demand that V be an LP, the natural LP condition is when you're working with particles in 3 dimensions, you want P to be bigger than or equal to 2. In 4 dimensions, you want it to be 4, and in 5 or more dimensions, you want it to be bigger than or equal to nu over 2. And it's known that if you take a minus x squared potential with C large, you lose self-adjointness, and you can check in terms of local LP conditions, that's exactly nu over 2. So it's not, it was actually believed at this point that this was the optimal condition. It was known as far as behavior at infinity was concerned, there's a difference between positive and negative parts of V. If, say, V is smooth, any positive V that's smooth leads to what's called essential self-adjointness, whatever that means, on the C infinite functions of compact support. But negative part, you need at least a condition that says it doesn't decay too fast at infinity. So when I entered the field around 1970, the general wisdom was that the right LP condition was the P condition I mentioned before, that V plus should be an LP loc, and V minus should also be an LP loc, but the norm shouldn't grow too fast at infinity. But fortunately, I was working in more than one area, and there was a method called the method of hypercontractive semigroups that was developed in studying quantum field models. And I realized in 1972 that using these methods, one could actually show that when V is positive, so long as V is in L2 with this Gaussian weight, then you don't need P to be bigger than nu over 2. P equals 2 is enough, even if nu is very large. The Gaussian restriction isn't very strong. That actually allows pretty crazy growth at infinity, but it still seemed unnatural. It seemed to be an artifact of the proof. So I conjectured that L2 loc should suffice. 3 weeks after I sent out my preprint, and you should realize that in those days, you essentially had manuscripts typed on ditto masters. You produced, Xerox was too expensive. You produced a limited number of copies of preprints, which of course you sent out in the mail because email didn't exist. 3 weeks later, I got a letter from Kato, and you have to realize that those 3 weeks involved sending a letter from Princeton to Berkeley, and his sending the letter from Berkeley back to Princeton. So he actually didn't spend the full 3 weeks. That proved my conjecture with totally different methods. I won't have time to discuss his distributional inequality and his simple proof of my conjecture, and the relation to comparison of semigroups and something called diamagnetic inequalities, but that's the other self-adjointness result I want to mention. Once one has some self-adjointness, one turns to spectral analysis. There are 2 ways of decomposing the spectrum that one initially looks at. One is called essential and discrete spectrum, and the other is the Lebesgue decomposition. So an energy E is said to be in the discrete spectrum if it's an eigenvalue of finite multiplicity. The essential spectrum is just the points in the spectrum that are not discrete spectrum. Physically, discrete spectrum corresponds to bound states, and essential spectrum involves states that can escape to infinity. In many cases, the essential spectrum is an semi-infinite interval, and the main issue is determining what the bottom of the essential spectrum is. Other natural questions concern what the information on the lowest eigenvalue, whether there is any discrete spectrum, and if there is, whether there are finitely many points in the discrete spectrum, or infinitely many. In quantum mechanics, or at least without electric field, the energy is always bounded from below, so if there is discrete spectrum, it has to be, it can only be countable converging to the bottom of this essential spectrum. The other decomposition involves what are called Lebesgue decomponents. A fundamental theorem in measure theory says any measure on the real line can be decomposed naturally into 3 pieces. There's a pure point piece, a sum of discrete point masses. There's an absolutely continuous piece, a piece of the form f of E dE. And there's a third piece, which is called a singular continuous piece. It's a measure which is supported on a set of Lebesgue measure 0, but it has no pure points. At first, it's shocking such things exist. The canonical example, of course, is the Cantor measure. Similarly, if you're given a self-adjoint operator, in particular quantum Hamiltonian, you can apply this Lebesgue decomposition to the spectral measure, and you get that the Hilbert space can be naturally decomposed into a direct sum of pieces that have a pure point piece, an only absolutely continuous piece, and a singular continuous piece. As I mentioned before, the pure point piece we think of as describing bound states, but it was realized in the mid-70s. There was also a possibility of dense point spectrum. I hope to get to that at the end. The absolute continuous states are traditionally associated with scattering states. The dynamics associated with a singular continuous piece would be somewhat strange, because it's known Fourier transforms of singular continuous pieces are kind of weird. For example, the Cantor measure, while in some average sense its Fourier transform goes to 0, it doesn't pointwise go to 0. There's a funny recurrence for the Fourier transform on exponential scales. So there was a working presumption that atomic Hamiltonians had no singular continuous spectrum. This is something that my advisor called the no-goo hypothesis. But the theory was, well, it isn't describing bound states, it isn't describing scattering states, it would be describing goo. Since we don't believe, we've never seen goo in atoms, there must not be any singular continuous spectrum. In a companion paper, so in the same issue of Physical Review, where his self-jointness result appeared, Katos studied bound states of the helium atom. Hydrogen's exactly soluble, but helium's not. So technically, from a mathematical point of view, before Katos' work, there was no mathematically rigorous proof that helium had any bound states. Kato proved there were infinitely many bound states if the mass was infinite, and he only proved 42 complete shells with the actual physical mass. The reason he didn't get infinitely many states in that case is he couldn't accurately describe the bottom of the essential spectrum. 20 years later, once we knew what the essential spectrum is, I wrote a little paper that noted that Kato's method actually proves all neutral atoms and positive atoms. Ions have infinitely many bound states. This had been proven with by more complicated arguments in the meantime by Ghislain. There's a general result for locating the essential spectrum of n-body Hamiltonians with two-body potentials going to 0 and infinity. It's due to Hunziker, but I realized important special cases were found slightly earlier by Ghislain and Van Winter, and I dubbed this the VHVZ theorem. It's a name that's stuck. Given a set of particles C, you let E of C be the bottom of its spectrum, the lowest energy. What the HVZ theorem says is if you have an n-bottom quantum Hamiltonian with two-body potentials going to 0, and you remove the center of mass motion, whatever that means, then the bottom of the essential spectrum's a half interval. The bottom of the spectrum you get by considering all ways of breaking the system into two pieces, and you look at the sum of the energies of those two pieces. Given that essential spectrum is associated with particles moving out to infinity, this is a physically obvious result. It's quite intuitive, but at least the initial proofs, while they were not hard, were not intuitive. They depended on rather involved integral equation expansions. In 1976, Enz and I found a proof using geometric methods, and around 2005, many groups found a very general theorem that explained what was going on. I'm not going to talk about that. So I want to say a little bit about Coulomb energies. So you let the h of z, n, and r1 up to rk be the Hamiltonian of k nuclei at positions rj. There actually are additional parameters, little zj. Capital Z is the total nuclear charge. The zj's are numbers that add up to 1, so you might have nuclei of different energies. You let E be its ground state energy, that's the bottom of the spectrum, but you don't want to consider it as an operator on L2 of all 3n particles. You want to restrict to antisymmetric functions of the x's. This is an expression of what's known as the Pauli exclusion principle or Fermi-Dirac statistics. And there's a little, it's not actually antisymmetric because you need to, there's a complication due to the fact that the electron has 2 spin states that I'm not going to try to explain. And E of Z is the symbol that one uses when you have a single nucleus that is an atom with n electrons, with Z, charge of nucleus Z, and n equals Z. In 1972, Lieb and I actually were able to control the large Z behavior of atomic energies. We proved E of Z divided by Z to the 7/3 has a limit as Z goes to infinity. We actually proved that a certain semi-classical theorem known as the Thomas-Furby theory was exact in this infinite Z limit, and we had similar results when n wasn't equal to Z, but rather n divided by Z goes to lambda. We also had results for molecules. Various people studied the next term, which is of order of Z squared, and Pfefferman and Zako even had results on Z to the 5/3. One is often interested in understanding what the dimension, how many bound states there are, counting multiplicity. So N of V is this number of, is the dimension of the negative energy states. It's called the number of bound states. There were early bounds in terms of due to Bogman, Calogero, Biermann, and Schwinger. But the most famous bound on N of Z is called the Zwickau-Lieb-Rosenblum bound, and it says that N of V is bounded by the nu over 2 power in new dimensions. Zwickau and Lieb were actually, I conjectured this, and it's famous in part because it has the large coupling behavior and it's quasi-classical. That is, if you look at the volume of negative phase space, it essentially has this behavior. Another famous quasi-classical bound is that of Lieb and Tiering. They involved sums of powers. When P equals 0, this is what I called N of Z. In general, you have a result of this form. It's also quasi-classical. For nu bigger than or equal to 3, as I already mentioned, this extends to the bound borderline case when P equals 1/2. It's also known to extend to the borderline case. It's false at the boundary P equals 0 in 2 dimensions. There's an interesting open question. In fact, there are several about the best constant in this bound. So if you go back and look at this bound, there's this constant. And there are 2 obvious lower bounds on this constant. It turns out that you can use this bound for a single bound state. So the bound tells you sometimes there are no bound states. That turns out to imply a Sobolev inequality. So the best constant in the Sobolev inequality, which is known, gives you a lower bound on the Lieb-Tiering constant. It's also known that in the infinite number of bound state limits, there's exact asymptotics, and that gives you a different lower bound. There was a short time that the belief was that the constant should be the maximum of these two known lower bounds. It was actually found not long after their initial work that in dimension 8 or more, this conjecture fails. But nu equals 1 is particularly interesting. In that case, the constant is larger. That shouldn't be 2, it's 3/2. The constant, the quasi-classical constant is bigger when p is bigger than 3/2. And the Sobolev is larger when p is less than 3/2. For the case p equals 3/2, the KdV sum rule implies a Lie-Thirring bound, so it's actually known the optimal constant for the case p equals 3/2. Eisenman-Lieb then says we know what happens for p bigger than 3/2. Hundertmark, Lieb, and Thomas proved the best constant for p equals 1/2. So a famous open problem where there's been no progress is to prove the optimal constant when p is between 1/2 and 3/2. It's also interesting to know what happens when nu equals 3 and p equals 1, because this is connected with the stability of matter result, which I'll discuss in a moment. Here, the best result that's known is due to Frank, Hundertmark, Yex, and Nahm. I'm going to say later about various results that were done in Sloan Hall. This was not done in Sloan Hall, it was rather done in the accounting services building. It was pointed out by Ansager in 1939. Ansager was a very interesting, originally Norwegian scientist who spent his career at Yale. He was a chemist, but was very interested in mathematical problems. He's perhaps best known in the physics community for solving the two-dimensional Ising model, but he got a Nobel Prize for work in thermodynamics, and he also asked the question that I'm about to tell you. My advisor, Arthur Whiteman, was an undergraduate at Yale in the 40s when he was a professor there. Whiteman once said he was notorious for giving a course on statistical mechanics and a course on advanced statistical mechanics. The courses were notoriously very difficult, partly because of the material, partly because of his accent, and they were known as Norwegian and advanced Norwegian. And he pointed out that it was very important to understand, to prove that if you had a Hamiltonian with lots of nuclei with charge Z and N electrons, then with the usual Coulomb potential, then the Hamiltonian should be bounded below by a constant multiple of N plus Z. So a basic point of quantum theory is that the uncertainty principle tells you that the hydrogen atom doesn't collapse. There's a lowest energy to the hydrogen atom. What Ansager pointed out is that's not actually enough. If you look at nature, it's true that when you put in lots and lots of particles with Coulomb energies, those also don't collapse. And that's really implied by a bound like this. Of course, if instead of having repulsive interactions, all the Coulomb potentials were attractive, then in fact you would have collapse. That's what produces black holes. So this is a very important basic fact about quantum mechanics. It's more subtle than even Ansager realized, is shown by the fact that it's actually false if electrons are bosons. So only because electrons are fermions does bulk matter exist. If electrons were bosons, matter would collapse and physics would not look the way it does. The inequality was actually proven by Dyson and Lieb in 1964. Their proof is complicated, is not very conceptual. Their constant is many orders of magnitude too large. In '76, Lieb and Turing found a much better proof, so much so that one doesn't really hear about the Dyson-Lennard proof anymore. This is one of the rare cases in mathematics where the second proof is what everyone talks about. Their constant is only off by a factor of about 30, and if one could improve the earlier thing, would be better than 30. In fact, it's better than 30 now. And their proof is actually quite intuitive. They first used a Lieb-Turing inequality with p equals 1 to bound quantum energy from below by a Thomas Fermi energy, by a quasi-classical energy, and then they used a result that was discovered by Teller, that in Thomas Fermi theory, molecules don't bind. There's also an issue about negative ions, energies. So you let delta Zn be the energy needed to remove one electron from a system with Z electrons, Z nucleus of charge Z and N electrons. To say this is positive is to say that the nucleus, you can always add one more electron. One might expect that you can't add in many electrons as you want, and in fact this was proven that there's a critical number of electrons that you can add. This was proven by Ruskay and Siegel. Lieb then found a very elegant proof that you can never add more than two Z electrons to a charged Z nucleus. And Lieb's, Siegel, Turing, and I proved that this N critical, in fact, divided by Z goes to 1. Again, this needs Fermi statistics. It's known the lim inf is strictly bigger than 1 for bosons. But in fact, in nature, there's no charge -2 negative ion known. So if you look at Z up to 92, this N critical is always either 0 or 1. So there's a natural open conjecture that there's some finite number so that this is true, and it could even be true that K is 1. Again, an open question for the audience to work on in their spare time. Okay, so that's what I want to say about bound states. I want to say now something about scattering theory and absolutely continuous spectrum. For two-body systems, it means that the AC spectrum, scattering states, means things that just look like minus Laplacian. This was proven to be, the existence was proven in the 1950s. Asymptotic completeness means all the absolutely continuous states are scattering states. This was proven by various people from 57 to 76. Final results were by Agmon and Kato Kuroda. Slower than r to the -1/2 means that doesn't include Coulomb. Whiteman had a PhD student named Dollard whose PhD showed how to modify scattering theory, and something's known in that case. I'm not going to spend more time on that. N-body's much harder because your scattering states can involve bound clusters. So you can have N particles moving freely, or if you have a 7-particle system, you might have 2, 2, and 3, or 3 and 4. There are many different scattering channels. For 3-body systems, this was first solved by Fadeev, but for almost 10 years after his work, the N bigger than 4 case was heavily studied. Several workers announced solutions only to later withdraw. At one point, Agmon remarked to me, those whom the gods would drive mad, they teach of the problem of n-body asymptotic completeness. It was finally solved by Siegel and Sofer. There are interesting questions associated with slower than r to the minus 1 decay. Much of the work has been done in one dimension. In 1982, in Sloan, I realized that if decay was slower than r to the minus a half, then in fact you could, and you had a random potential, then you'd get no AC spectrum. And so by 1995, people were very interested in what happened between decay a half and decay 1. This was a local sport, and Kiselev, Killip, and Lukic in their PhD theses actually made significant progress. The best result was by Dave and Killip, who proved in the L2 case, you always had some AC spectrum, and there's a natural open problem, which is vulgarly known as Simon's conjecture. What's the analog in new dimensions? Again, I know actually at least 2 mathematicians who've worked really hard on this problem, and it still remains open. Next, singular continuous spectrum. So Whiteman's no-goo hypothesis. I think I'm going to skip most of this, except to say that it was essentially solved for faster than r to the minus a half conjecture. But I like to joke, I spent the first half of my career showing singular continuous spectrum isn't present, and the second half showing that it generically is. The first hint that this was true came for what are called sparse potentials, a remarkable paper by Pearson. By the mid-1970s, there was an explosion of papers, mainly from Sloan, and I proved a result that said a generic potential in some sense decaying like faster than r to the minus a half actually has purely singular continuous spectrum. So there are interesting results there. I'm not going to talk about mixed spectrals because I do want to get to the final 2 things. By the 1930s, physicists understood when then V is periodic, you have plane wave solutions. And there's a lot of literature on that. As I said, I want to get to the last 2 topics, so I'll skip this issue. And I'll talk about the last subjects, which are random and almost periodic. It's very useful to study, to use Markov's dictum, be wise, discretize. So most of the literature on these random and almost periodic problems have considered the operators not on R nu, but on Z nu, where L2, little L2 of Z nu. So H0 is then just a hopping term involving nearest neighbor interactions. V is a diagonal matrix. The simplest random model is where the potential, the value of the potential at individual points are independent, identically distributed random variables, uniformly distributed in an interval. This is often called the Anderson model. It is a random model, but it's very different from a random matrix, and I want to emphasize that. The spectral theory is very different. Phil Anderson, in fact, got a Nobel Prize in 1977 for his 1959 work, where he intuited what randomness would do to quantum mechanics and suggested that you would have localized states in that problem. His paper was hard to understand, and when I was visiting
IHES, David Ruel, told me about Anderson's work and said probably there was singular continuous spectrum, but in fact the first rigorous proof showed in a slightly different model that in fact the spectrum is in an interval, but it's dense point spectrum. It's not singular continuous. States are exponentially localized. There's a useful way of seeing when you get localization that I found with Tom Wolfe. There are two methods that have been invented for handling localization in more than one dimension. It's known at large coupling or near the edges. One is due to Fröhlich Spencer, and the other was developed in Sloan Hall when Michael Eisenman was a Fairchild scholar. But this remains one important question on localization. So in one dimension, we know that one always has localization, and it is believed that in the Anderson model, for the two-dimensional model, one also always has dense point spectrum, localized states. This is an open question. Perhaps the most famous open question in the theory of Schrodinger operators involves extended states. So there's an open problem in 3 or more dimensions. Prove that for not large coupling, not at the edge of the spectrum, there exists an energy regime that has absolutely continuous spectrum. And related is to prove that unlike for scattering states, the expectation value of the mean square grows like square root of t. So this is dispersive relations. So that's very hard to imagine solving that without solving the other open question. And in my last 3 minutes, I want to say something about absolutely continuous, almost periodic potentials. Simplest example is on L2 of Z, where you take a potential which is a pure cosine, but the frequency is irrational, so the potential is almost periodic rather than periodic. It looks a little like the Matthew equation, so I called it the almost Matthew operator. It's a name that's stuck. And I think it's correct to say there have been more papers in the annals over the past 25 years on this object than any other single, not subject, but single mathematical object. There probably are 15 papers on the annals on this model. Among the results there's something called the 10 Martini Problem, which is that this model has a Cantor spectrum. I won't tell you where the name comes from, but you can look at the slides. This was eventually the final result. The full result was proven by Avila Zhitynskaya. And there's something called the Hofstadter butterfly, which is very famous, that shows what the spectrum looks like. There are results on the measure of spectrum. And again, I'm not going to say a lot, but there's a natural open question. At coupling 2, the spectrum is known to have measure 0, so there's a natural open question about what its Hausdorff dimension is, which should be alpha dependent. It's interesting that in fact the spectral properties of these operators depend on the arithmetic properties of the frequency. This was originally suggested to me by Sonak, and motivated by his suggestion, Avron and I proved the first such results. There's now a lot known about this problem. There's a spectral transition result. There were a number of open problems on this almost Matthew problem. They were all solved by Avila, and his Fields medal partly mentioned this work. One thing I've learned is it's important to advertise. So I always end my talks these days by telling people, since not everyone knows, it's now almost 3 years ago that the AMS published a series of works of mine that I want to make sure everyone knows about. It's entitled A Comprehensive Course in Analysis. There's real analysis, basic complex analysis, advanced complex analysis, harmonic analysis, and operator theory. Thank you.
Questions, please. Barry, you didn't mention solitons, you didn't mention inverse problems.
Correct. That's absolutely correct. Although in the periodic slide, I did mention in passing that there were results in the. You're absolutely correct. As I said, there are many interesting questions connected with inverse theory, and the study of the one-dimensional periodic problem turns out to be just remarkable. One other subject that there is almost no work on, but is motivated by this, is that I've begun to look at is periodic problems on trees, where there's again a really fascinating set of open problems. There, again, since there are no results on that subject, but there are 3 results, but there are almost no results. I didn't even discuss that, but that's correct. There are lots of things I didn't discuss. I squeezed an awful lot into 50 minutes. After all, that was only 1 minute per year.
You could have done 70.
You didn't give me 70 minutes. Yes, it's true. I could have done 55 even.
So what did you do with Tom Wolfe you mentioned in the Anderson model?
Correct. So what we proved, so basically what for example Froelich and Spencer had at that point proven is certain L2 results on the Green's function. And it turns out that that implies exponentially localized states, and that follows with the work that Tom and I did. So there's a lot of fascinating stuff that happens for rank 1 perturbations. So Tom and I sort of understood one aspect about what happens, and in fact there's also a paper that I didn't have a chance to mention by Del Rio, Nick, and I that has a different aspect that has to do with this generic singular continuous spectrum. So there's a lot of general results about rank 1 perturbations that were done in Sloan. I was very fortunate to have 2 very strong analysts as collaborators on the 2 different aspects of that.
Any questions? So let's thank the speaker again.